These notes here should be a recap from last year. Root A only exists when A is greater than or equal to 0. It's only real if A is greater than or equal to 0. There are a group of numbers called imaginary numbers which let A go into the negative, but they are only in spec maths, not methods. If we have a number under a square root, we can split it with a multiply. We can't split with plus or minus, but we can split it with a multiply, and we can split with a divide. And these are a set of numbers. You can always think of them as another set of times tables that I kind of expect you to sort of recognize. 2 squared, 3 squared, 4 squared, etc. And those numbers keep coming up again and again. All right, so good information to have. A square root is actually got a little 2 up there. So this is actually the same as that. We just never write the 2. But really, there is a 2 there, and it means the power of a half. So if there is a number under that, it's really to the power of a half. If you ever see a cube root, or a 4th root, or 5th root, it means a power of a 3rd, a 4th, a 5th, etc. So just some notation. And that is sort of useful for letting us resolve this type of thing. The cube root of 8 to the power of a half. Now, 8, we might think of something to do with 2. We can think of that as 8 to the 3rd to the power of a half. Are we happy that 2 to the power of 3 is the same as 8? Because it's like 2 times 2 times 2 gets us the 8. Cool. So I can replace that 8 with 2 to the power of 3 to the 3rd to the half. And all I've done is I've pulled out that 8 and made it 2 to the power of 3. Kept the 3rd above it, kept the half above that. Now from Surds rules last year, power to power multiplies. So this is really 2 to the power of 1, because 3 times a 3rd is 1. To the power of a half is 2 to the power of a half, or it could also be written as root 2. So just reminding you about notation and the odd surds rule. And today is essentially a practice of some operations with surds, and then practice of index rules that you'll have done last year. So, first up, simplifying surds. In this case here, there's not a lot we can do with root 6 or root 11. They're as simple as we can make them go. If we're asked to simplify this expression, the best we can do is collect like terms. 5 root 6's, take away 2 root 6's, you'd be looking at 5 take 2 is 3, so 3 root 6's. You can underline the like terms if you'd like. Followed by the root 11's are also like, and in total there are 7 root 11's. And you can't go any further. It's unlikely you'll ever see one as neat and simple as that, but it's important to know that there is possible to stop without being a single term. Alright, next one down is a little more complicated. A good first option in all of these is to simplify the square roots where possible. So, what is 3 root 49?
21.
Good. Root 49 is 7. 3 times 7 is 21. Plus. Now, any guesses what we could do with 288?
Well, it's 1 times.
Yeah, I probably haven't continued my list enough, have I? We're feeling like we can use that. So instead of 2 times 2 root 88, I would write it as 2 times root 144 times root 2. So we've split the 288 into that combination. And it's going to work out nicely to be 24 root 2. But I won't write that to the next line. Take root 144 is 12. Take, what do we do with 2 root 18? There's still a 2 there. 18 has a 9 in it, times root 2. So we're looking to pick out these numbers because they're the ones we know simplify under a square root neatly. And so if I was going to simplify this further, it would be 21 plus 24 root 2 minus 12 minus 6 root 2. Because 2 root 9 is the same as the 6. Then we're collecting like terms, so the whole numbers together, the root 2's together. 21 take 12, what's that, 9? 24 take 6 is 18, root 2. And that's as far as we can go. So we're looking to simplify each of the surds, and then at the end collect like terms. Alright. Here, when we're multiplying, we can do things in any order we want. Really, there's a little multiply sign in there. That reads 4 times root 15 and 2 times root 18. But if I were you, I would rearrange this to split it up into things that are going to be useful to us. So I'll try to show you what I mean. I want to do 4 times 2 at the start, because that's nice. I can do 4 times 2. I can't, well I probably could, but I don't, let's say I don't want to do root 15 times root 18, because 15 times 18 is not pretty. What you'd really do is you do 30 times 9 and get root 270. But let's say we don't want to do that. Instead, you notice how these have a common factor of 3? I would write the root 15 as root 3 times root 5. That 3 and the 5 make the 15. The reason I've left the gap is because I'm going to split the 18 into a root 3 and root 6. And I've written them out in this order just to make my life easy. 2 times 4 is 8. Root 3 and root 3 gives us the 3. So now it's 8 times 3. 8 times 3 is 24. Root 5 and root 6 is root 30. And I can't pull any of these factors out of a 30. So that's as far as we can go. The answer is 24 root 30. Cool thing is, you can put that in your calculator and it will just spit out that. Or you can put that in your calculator and it will just spit it out. But ideally, we'd be able to manipulate them by hand as well. All right, turn it over. Wait, before I go on, is that all okay? Cool. All right, root 3 to the power of 4. There's probably a couple of different ways you can think about this. You can either think about it as 3 to the half to the power of 4. 4 times a half is 2, so 3 squared is 9. Or you could think of it as root 3 times root 3 times root 3 times root 3, and you know pairs of them make 3, so it's really 3 times 3 is 9. Not fussed which way you think about it, but either way, you're ending up with a 9. It's another pretty quick one. So again with multiplying, I'd multiply the numbers together and the roots together. The numbers together is 2 times 3, so 6. What's root 5 times root 20?
Root 100. Root 100?
Yeah, root 100, which is 10. So it's really 6 times 10 will give us an answer of 60. And with some practice, you guys will get pretty speedy at doing these. Alrighty. Here, a number of different ways you can go about it, but if you have a surd over a surd and you can find a common factor, you can cancel them down. So between 75 and 20, it feels like we should be able to pull out a factor of root 5. So 5's into 75 is 15, so I would write that as root 15 times root 5 over 3 times root 4 times root 5. And when you have the same root top and bottom, you can cancel it. Root 4 is 2, so it's root 15 on 6. And we can't do anything with the root 15 or the 6, so it's as far as we can go. I think probably the most tricky thing about this is figuring out when to stop and not do other stuff. Alright, any ideas where to start here? Yeah,
Do the 90 and get 3 square root of 10.
nice. So 90, or root 90, is the same as root 9 times root 10 is the same as 3 root 10. So really this is 12 plus 3 root 10 on 3. Now we can take out a common factor of 3. So you can think of this top as 3 bracket 4 plus root 10 over 3. And you wouldn't have to show that step, but you're reminding yourself that you're taking a factor of 3 of both of them and then cancelling it, and the answer will be 4 root 10. But you'll be completely forgiven for just going from here to 4 root 10 without showing the 3 going anywhere. Alright, last little skill before I leave you over just to do some revision and practice. Rationalize the denominator and simplify. In maths, we often don't like having irrational denominators. We don't like having the roots down the bottom. Instead, we use a trick called multiplying by 1 to rationalize the denominator of both and from there solve it. So, to rationalize the